Okay, so just continue. Okay, so when you generate the signature of each document, then we can compare the signature between each document. And here is just an example. Okay, so we have, you can imagine that we have a signature matrix. Okay, the rows are your signature, the mean hash values, and the columns are your documents. Okay, you have such a matrix, and you can do the computation, just compute the pairwise similarity between each signature columns. Okay, in the above scheme, we will choose k mean hash values independently, and it means you need to prepare k different hash functions, or to do the k different computations, okay, shuffles. And an alternative way is maybe we can use only one single hash function, only one, and then we will perform one computation, only one computation. But for each rows, we will pick k smallest hash value. Okay, so the idea is like this. Okay, so suppose I have this computation here. Okay, I want to pick the two hash values. So here, after the computation one, after the computation, okay, for C1 document, I can pick the second is the first hash value, right? And we continue to pick the next, the third. Okay, so I will pick 2 and 3 as my mean hash values. Okay, just use one computation, but I can pick how many the k smallest values as you want. Okay, so it looks very more efficient, right? Okay, the idea is, but the computation between the two documents will be more complicated, like this. Okay, here is if we compute the similarity between the I and the J's document, we take their signature. Okay, here is the intersection. You see signature I union with J. Here means the k smallest element of Ci and the union Cj. So it means you have to union Ci document and Cj document, and to calculate to extract the k smallest mean hash values. Okay, so you generate these signatures and intersect with the signature I and the signature J. Or it's more complicated computations. Okay, it's called an unbiased estimator. And there's a biased approximator, and I will give you a range. So it's the similarity between Ci and Cj is between the two in the interval. Okay, the interval is actually exploitation of the signature I intersect with signature J. So if you generate your signature in this way, okay, the computation is more complicated like this. Okay, I give you final remarks you can take away for mean hash. Alright, so to reduce the probability of false positive and false negative, we can collect k signatures by repeat the commutation k times, or to pick the first k commutation rows. Okay, so there are two ways, but the computation of the similarity are different. And if you choose a large enough, a suitable large of k, the number of false positive will be very small, and the false negative is almost zero. Okay, so it's for the topic of mean hash. Any problems? Alright, so let's go to the next topic. is about the LSH. Okay, mean hash. Okay, so actually, all right, this can fit in your memory because it's more compact. So you can load all your matches into your memory. It's okay. But if we want to compare, to find a similar set, okay, remember our goal is to try to find a similar documents from a very large data set. Okay, so if we want to compare, want to find the similar pairs, it still takes too much time if we just take any two of them to compute the similarity. We still have, you know, there's a very big combination. Okay, so it still takes you a lot of time. So that's why we introduce the locality sensitive hash. It's called LSH. Okay, so the general idea of LSH is we want to generate from your large collections and from it to generate a small list of candidate pairs. Only these candidate pairs need to be checked for their similarity. Others, we just ignore them. So it's actually like to build an index structure. Okay, based on the index structure, you just only to check a very small number of candidates. All the others you just skip. You don't need to perform computation between them. Okay? So the LSH the idea is to generate a small list of candidates from your large data set. Okay, so let's see how to make it work. Okay, so first we have to pick a similarity threshold T. The T should be smaller than 1. Okay, so T is a similarity that you hold. If the document their similarity is above the threshold, it should be included in your candidate. That's my idea. So you can set T to be 0.5. So it means if the two documents their similarity is above 0.5, then these two documents should be picked. It's my candidate. Oh, it's my motivation. It's our goal to design the LSH. Okay. So we want to compare the two documents, CI and CJ. Okay, so that if they are picked as a candidate pairs, if and only if their signature agree at least fraction T, like 0.5. Okay, they have a 50% similar, so that they should be picked based on our LSH mechanism. They have to be picked as our candidate. Okay, so the general idea of it is like this. We will hash your column of signatures several times, and if any, and we will arrange the similar column to hash to the same bucket. And if they any of one, at least once they are collide in the same bucket, we will treat them as the candidates. It's a general idea. Okay, like this. So because we have a very big matrix here, okay, the binary matrix. Okay, the column means a document. Okay, and we have several shingles and signatures. They are already in hash values. Okay, so suppose we have 100 in hash values. And this is some document here, and I divide the signature into 5 bands. 5 bands. This means each band it contains 20 min hash values. Okay, 20. In total, 100 min hash values. Okay, so it's my design like this. So it's so how many bands you want? It's your hyperparameters. You have to choose. You have to set by yourself. Okay, let's check for the second rows here. For the second batch, in the second batch, here there are several rows here. Oh, in our case, if there are 20 main hash values in the bank. Okay, so there are 1, 2, 3, 4, 5, 6, 7. There are 7 documents, and we check this second bank. In each bank, it contains 20 main hash values. Okay, and we just use these 20 main hash values to perform a hash function. Based on hash function, you just calculate a new hash value. For example, this one, for your first document in the second row, sorry, in the second batch. Okay, its hash value will be here. You can think it's a bucket. There are several buckets. You just map it into a bucket ID. Okay, so the first document is mapped to maybe to a 10, number 10 bucket. And for your second document is mapped to maybe 200 bucket. The bucket ID is 200. Okay, and you can see that the sixth document here, so the hash function is also mapped to the same bucket. So it means the document 2 and document 6, they have the same hash values. They are collide here. Okay, so we can use this because they are collide. They have the same hash value, so we will treat the second and the sixth document. They will be our candidate. They have to be checked. Okay, so the same situation for the fourth and for the seventh document. Okay, both two they map to the same bucket. So it means I have to check. I will pick them as our candidate pairs and check it later. And all the others, they don't have the same bucket, so we can just ignore them in this row. Okay, any problems? 好，就是说每一个向量每一个向量就透过一个 hash function 就可以算出一个 hash 的值方位，然后它们就会对应到不同的编号。那如果说这像第二个跟第六个，它们的 hash 值是一模一样的，那我们这两个就要跳出来，就是当做我们 candidate 候选人，好，就是之后要再检验，因为它们可能相似度会很高，所以我们就特别把它挑出来。好，那其他的都没有对到，那就不用管它了，就这一回合就他们都没有，就都可以不用忽视不管。好，那当然我们还会有继续再往下做，那每一个回合都会去检查，到底哪一些可能会是那个相似度高的，就把它挑出来。好，只要有 collision 就会把它挑出来。Okay, any problems? Alright, so and now we give another example here. Okay, suppose we have 100,000 columns. Okay, means we have 100,000 documents here, and each one we have 100 signatures of the main hash values. Okay, so we can treat it as a 100-dimensional vector. Okay, with the integer. Okay, means the main hash values. Okay, so signature only take 40 megabytes. It's not very big, right? You can load all of them in the memory. And now our purpose is I want to get all the 80% similar pairs of the documents by using my LSH. If their documents, their Jakarta coefficient is more than 80%, they should be checked. I should pick them as a candidate. Alright, so if you don't use any technique, you just use the brute force exhaustive search. Okay, you have to so many pairs to compute their hash values. You see, it's a 5 billion pairs. You just pick any two of them to compute their similarity. So the combination is so big, right? Okay, so it's inefficient. Okay, so by using LSH, okay, we can reduce the number of computation. Okay, because it's like an index structure. It can help you to extract the candidates. Okay, so here we use 20 bands, and each band contains just 5 integers. Okay. Okay, now we consider the first case. Suppose the C1, C2, they are 80% similar. Okay, so it means the probability of the C1 and the C2, they will be identical in one band. What's the probability? You know, it's each band it contains 5 integers, right? I have R1, R2, R3, R4, R5. Okay, there are this is one band. In one band, I have 5 integers, 5 in hash values. Okay. Okay, so there's another. It's another document. Okay. Then I check if they are the same. R1 is R1 equal to S1, R2 equal to S2. All are the same. Then they will generate the same hash value, right? The same hash. They will map to the same bucket, right? The same bucket. Okay? So what's the probability? They have all the same. R1 is equal to S1, R2 equal to S2. All are the same. What's the probability? It's calculated like this. Do you agree? Because we assume that C1, C2 they are 80% similar. Okay, so we can assume that each pair they are similar is 0.8. Okay, so I have the similarity 0.8. Each one, and but all the 5 should be the same. The probability is just time all of them together. So it's over here 0.8 to the 5th. Okay. So the probability is 0.328. Okay. This means all the five values are the same between the two documents. Okay, so that they will map to the same bucket, right? And then next, I want to calculate if C1 and C2 they are not similar in any of the 20 bands. Recall that if any bands we have five hash values, right? And but we have 20 bands. Okay, so there are 20 bands. This means for the 20 bands there's no any bands they are the same. Okay, suppose it's the first band, Okay, so the probability in this band they will not the same. Probability will be 1 minus 0.328 bands. Okay, so this is the probability that the 5 pairs are the same. If they are the same, they are not the same. The probability is 1 minus, right? Okay. This means in this band, they are not agreed. They don't have the same bucket. They do not hash to the same bucket. So the probability is 1 minus 0.328. Yes, and there are 20 bands. All the 20 bands, they are, no of them are the same. They don't have the same bucket. It means I tried 20 times, but every time they don't have the same bucket. The probability will be 2 to the 20. Okay. So the probability is very small. It's just only okay. It's 0.00035. Okay, very small. Right? Just okay. Okay, so what's the meaning? It means they will not be, because in our in our LH design, if I can map to the same bucket, I will take them as a candidate, right? So anyone from the 20 bands, any bands, if I find they can map to the same bucket, I will take these 2 documents to be candidates. Yeah, but if something happens like this, all the 20 bands, they don't have the same bucket. Okay, so the probability is very, very low. So it means this has a very high probability. At least one bucket will have the same, will be the same among the 20 bands. Okay, so you can convert it. This means it has a 0.99%, and 99% this document C1 and C2 will be P, because at least one band they will be the same. Okay, so it will be P, and as a candidate, the probability will be 99%. Okay. 好，这个意思就是说，这两个 document 他们是80%相似，好，所以他们如果说在80%相似嘛，所以说他们这每一个 band 是有5个数字，那这5个数字都一模一样的几率只有0.328，好，那只要他们都一样的话，他们就会被我挑出来做候选人，好，那可是现在有20个 band， 好，这是第一个 band。第二个 band， 假设这20 band 都没有任何一个 band 是相同的 bucket 的话，它的几率会多少？只有这么低而已，对吧？这是1/3，那就表示说你有99.99%的几率，99.999%的几率会被挑出来，因为不可能20个都不会对，一定会有至少一个对，对吧？所以表示说，这个80%相似度有这样子的 documents， 它有0.999%的几率会被挑出来当做候选人。这个就是我们想要的，我们就是希望相似度高的被我们挑出来当做候选人。好，所以它不会被挑到的几率非常的低。OK。So it means because C1 and C2 they are very high similarity, so we hope they should be take as our candidates. So the probability they will be picked as a candidate is very high. It's about 99, more than 99%. Okay, so it looks good in this case. Okay. And the second case, if C1 and C2 they are only 40% similar, we don't want to take them as a candidate. Okay, because they are very low. Okay, so what's the probability they will be picked as a candidate? We can calculate again. Okay, so first, the probability C1 and C2, they are in one band. They have the same, all the five values, they are the same. The probability will be like this, just 0.01. It's much lower, right? Compared with the previous one, it's higher, much higher, right? But now it's lower, only 1%. It means that 1%, the five pairs are exactly the same. Okay. And then the next, the probability C1 and C2, they will be identical at least one band. What's the probability? It's very low, only 20%. Only 20%. They check 20 bands, they have the same bucket. Any one, okay, only 20%. So compare with, they have the 40% similar, but in LSH, they have 20% to be picked as a candidate. So it's much lower than their original similarity. Yeah, so it's not what we want because it's a low similarity. So we don't hope they will be chosen as a candidate. So probably very low, only 20%. Okay, the calculation is actually a binomial combination. Okay, so I can calculate for you. Just review recall your combination and the computation. Okay, the computation here. Okay, this can be expressed. This one is a combination. It means that C N is also can be expressed like this. So we can check the. Okay, we want to calculate at least one of the 20 bands. Okay, so we can see if they are one band, the same. Like this, they are all the five values are the same. They are one band, exactly one band, the same. What's the probability? Okay, the probability would be, you can choose, there are 20 bands, right? You can choose any one for the bands. And then the probability will be the same as there are one band, exactly all the five values are the same. It's here. And times with they are not the same. Okay, so they are not the same the probability. Okay, you will have a 99%. These five values do not agree. Okay, they have 19 bands do not agree. Okay, so you can calculate this. It's very close to 1. Okay, so I just write. It's very small, 0.99, but to 19, it's very small than So but to make the computation easier, okay, I just treat this as 1. So probability will be like this. Okay, it's exactly 1 bank. Identical. Okay, so then we check the second. If there are 2 banks, 2 banks is the same. So you can choose. This is right here. If there are 2 banks, you can choose from the 20 banks any 2 of them, and the probability will be like this. They are exactly 2 banks, the same, and it's a 20. Okay, it's a very small. It's a box. It's very small. Right? It means exactly 2 banks. Identical. Okay, just continue because we have to summarize all the possible combinations. Okay, so you can continue to I3. Okay, so you have to compute. You just derive by using these equations to expand it. So but it will be getting smaller, very small. So that's why we can roughly calculate it at 0.2 of all the summation of the 20 banks. Okay. Okay, so it's for your reference. Okay, we call it a binomial distribution. Okay, so for such a case, we treat this case because only 40% similar, so we don't want to retract it as our candidate. So the only 20% will retract it. So the false positive. Okay, false positive means we think this candidate should be candidate, but it's wrong. But the answer is wrong. So it's called a false positive. We think it is correct, but the actual answer, the real answer is wrong. So it's false positive. Means that we pick it as a candidate. The probability is just only 0.2. Okay, it's lower than its original simulation. So it's a good property. Okay, so you can see the LSH has a very special property like this. In our goal, we hope our LSH should be like this. Given your threshold T, for example 0.5. In 0.5, okay, so if your probability is below than 0.5, the probability to be chosen as a candidate should be 0. Here is the probability of the bucket to be picked as a candidate is 0. If lower than some threshold, like 0.5, should be 0. But if the threshold similarity is higher than the threshold, it should always be picked 100% as your candidate. So it's our LSH design, our goal. OK， 好，这个意思就是说，我们希望这 LSH， 只要你的这两个 这两个 document 它的相似度是低于0.5的话，它就不可能被我挑出来，被我挑出来几率是0。可是如果是大于0.5的话，它被我挑出来的几率是100%。我希望 LSH 要做到这种效果。好，就是 candidate 要被我挑出来。好，那之后我会再做更详尽的运算，更精确的运算，算那个转 class 没问题。好，因为那个算那个就很耗时。可是我挑这个很快，挑 candidate 非常快，很快就可以把要挑的就挑出来。那只有这些嫌疑犯才再去检查。好，这是我的目的。好 ，LSH 就要做到这种事情，就像锁链结构这样。好，要非常精确的抓到这些嫌疑犯。Okay, so this means LSH, and we hope the design of LSH can be very accurate, capture the candidates that with a high similarity. Okay. So it's our ideal case, but how about in our design? In this design, the actual its performance it looks good. Actually, it performs good, although it's not. It's also close to our ideal case. Okay, so you can see the red line. Actually, it performs like this. Let me show you the detail. Show you the analysis. So first, the overloads of a band are equal. Its probability is this, right? S is the similarity between the two documents. Okay, R is how many mean hash values in the band. For example, here are 5. Okay, you can recall to our previous example. So this means all rows of a band are equal. All mean hash values are equal in one band. And but next is some rows of band are unequal. Okay, so just use 1 minus this one. This means so there are some of them they are not equal. Okay, so it's a 1 minus SR. Okay, and the next is the green part. This means you see we have B. B is the number of bands. This means no bands identical. There are 20 bands, and all the 20 bands they don't have the same bucket. Okay, so you will have the probability like this. And finally, the purple, this one, at least one band identical. You just put 1 minus this. This means I just use the probability. This one is no band identical. So at least one identical. Just put 1 minus this probability. Okay, and this probability is curved. It belongs like this. And here is the T. T can be okay. T is actually, in this case, T can be computed. It's close to the 1 over B to the 1 over R. Okay, this example show you here for B is 20, R is 5. We have 20 bands. Each band contains 5 values. Okay, so the T will be calculated like this, 0.5, close to 0.5. And this means we hope if the documents, their similarity is higher than 0.5, it should be 100%. We hope 100% to be tracked as candidate. Okay, otherwise to be 0% to be tracked as candidate. Okay, so it's a result. You see, if the similarity is 0.2, the candidate to be picked, the probability to be chosen as the candidate A here is very low, right? If only 3, also very low. If the similarity is 0.4, still very low, right? 0.5, okay, it's a half to be peak. And if 0.6 is burst, the probability burst to 0.8. 7, 0. If 0.7 similar, the probability to be peak is close to 100%. Any problems?
对，就是我们说那个有个文件有80%的相似度，两个文件有80%相似度，代表说，那两个文件的 vector 的任一个数字，它们相似的几率都是80%。
就是以虚构的这种虚构的那个重叠性来讲，就是说你这些文件都已经把它转换成是虚构的。
对。
那虚构的话，那基本上虚构就是跟你那个文字的那个，就是从文字那边取出来的。对不对？所以如果说他们有88%相表示他们有80%的虚构是一样的。
所以代表说就是虚构是很多个数字嘛？
对。
那就是说每一个数字，两个文件之间的每一个数字，它们的相似度是就是一样的可能性都是0.5，就是都是那个相似度这样。
对。因为我们都把虚构转换成数字，你也可以想象成是。在这里就是一个的集合啦，那每个集合都会转换成一个数字啊，那这两个数字会一样的机会是多少？就跟他们的刚才前面有说，他们的这两个配序值，这两个虚构的配序值会一样的几率，就跟他们大图的那个相似度是一样的。那这个相似度就是算它的 Jacob coefficient，就两个集合的相似度也算是一样的，我们就把它转换成就是这样整个过程推导下来，其实把它转换成就是这边的 similarity 的意思，其实原本是指的是两个大图的虚构 set， 两个集合的相似程度，但是已经可以对比成就是他们的 hash 的值会相同的几率是多少？好，就是从前面一系列讲下来，就是给你这样的一个思维。Okay, any other problems? Alright, so it's a summary of our algorithm. Okay, so here, first we divide the matrix N into B bands, and each band contains R rows. And for each band, we just hash this portion with K buckets. Okay, and then we can retrieve if any column pairs they have the same bucket, they are hashed to the same bucket, we will retrieve them as a candidate. Okay, and finally, you can kill the B and the R because you modify, they are the hyperparameters. Okay, you modify them, they will generate a different threshold. Okay, you can tune it so that if for example you want your T is close to 0.5. Okay, you can choose T is 20, R is 5, like this. So if you want your T to be 0.7, okay, just tune it. Okay, so the T can be approximated by this equation. Okay, so this LSH, okay, is an idea. It's if you can try to just tune the hyperparameters so that you can almost get all the high similar signatures, but low similarity signatures are ignored. Okay, so it's the main idea of the LSH. It works very well. Okay, then for all, just we only need to check a very small portion, a small fraction of candidate pairs. Okay, then we check, we do the re-ranking again, compute the exact similarity. Alright, so it's is a final conclusion. So LSH tend to produce more false positive or false negative. But alright, so sometimes it will generate, because it generates some candidates. The candidate may not be your correct answer. Okay, it's just candidates. Okay, but you can do the ranking to compute their similarity in a more detailed way again. Okay, so although you can maybe generate some false results, yeah, but the main advantage is you can reduce your space and time for in your computation. Okay. So it's a general idea or the main concept of LSH you should take away. Alright, so then we go to the next topic. Okay, the next topic is use hashing for binary embedding. Okay, the idea is that our motivation is trying to find a similar set from a data set for a given query. In our previous topic, we want to do the data mining, right? We want to find a similar set from a large database. But now, this is another way, another view to think about your large database. I give you a query. Please find my neighbors, my similar documents that are very close to the given query. Okay. So there's some applications you can use it to find some near duplicate or copies from your data set. Or you can use it to do clustering, to do recommendation, or to do information retrieval. Okay, here is the reference I will talk about. There are some papers. You can see such a hashing technique to generate the binary code already, I think it's 10 years ago technique. But until now, there are still many papers try to address these issues. But they shift to like the closed model issue. At least I think most papers they put focus on closed model issue. Before we only focus on only one modality, but now they consider multiple modalities. So I will review some recent papers using deep learning, but it's not updated only to 2020. But in my paper list I show some papers they are doing hash. So if you can choose it as your presentation paper, okay, I would be very appreciate. I appreciate if you can choose so that I can update my slide. Okay, so first we talk about the nearest neighbor search. Okay, so just to recall your memory, refresh your memory. So here you can see we have many data points here, and they have different classes label. I use different symbols to represent their corresponding label. Okay, so you can see there are some label belong to close, some is a circle, and some belong to a diamond. There are three different classes. Okay, so here I give you a query. This one is on my query, and I have a search radius here, and inside the radius I find three data points as my nearest neighbors. Okay, so you can see two of them are close, and one of them are circle. So I can use this to do classification. Right? I just do the voting because the three of them, two of them are the circle. Sorry, two of them are close. So I think this query should belong to the close class. Although its location is inside is a circle class, but with the voting mechanism, okay, maybe I can pick a fair judgment Okay, so to determine its classification. So this way is called a nearest neighbor classification. Okay, so it's also application by using the nearest neighbor search to determine your classification result. And now we mainly put focus on approximate nearest neighbor search. Okay, because the inductive search is infeasible. Okay, as your data size is getting more to billions to trillions, it's too many. Okay, and then also your dimensionality is getting higher, from hundreds to thousands. It's getting higher. Okay, so you have the computation resource is too big. Okay, so considering the storage and the computation, so we should use which may not use the exhaustive search. Okay, so an alternative way is use approximate nearest neighbor search. Okay, the approximate nearest neighbor search will actually divide their approach into these types. Okay, first, from the view of the index space, okay, you can see they can use tree structure or IBM inverted file structure or the graph structure. Okay, I have mentioned it in our previous lecture. And for the compression-based view, okay, we can divide into two types. One is the product combination, and the other is the hashing, or we call it binary embedding. So today's topic will focus on hashing. Okay, so in hashing, the idea is we will repeat to do the partition space, and each hashing we will divide the space into two parts. Right? You can imagine that we have a hyperplane that divides the space into two parts. Okay, so each part will have one part is belong to bit 0, another part belong to bit 1. Okay, so it's because one hyperplane can divide the space into two words. Okay, the one word is 0, encoded as 0, another word encoded as 1. So it's the general idea of the hashing. Okay, so here the hashing is used to divide your space, not used to check to consider your collision, or we use it in another way. Okay, so the data, each data you can, according to its space, which word it belongs, you can assign a binary bit to it. So you can repeat it several times. If you have many hyperplanes, okay, so for example, 100 hyperplanes, so you can use 100 planes to generate 100 bits. Actually, it becomes a binary code. So every data, you just check it belong to, check with each hash functions, then you will know which bit it belongs to assign to its binary code to each data. Okay, so the pipeline for the hash-based AN search, there are 3 steps. First, we design a hash function. Okay, so the searcher design can be used learning based or just random to generate a hash function. And then the second, you use the hash function to generate the binary code, and according to the binary code, you can generate the index tables to do your index. And then the third is for the online search. Okay, give a query, then the query will also do the hashing, then use your index table to find your result. Okay, so to design your hash functions, okay, there are two ways. The first way is randomized hashing. Okay, so later I will introduce two randomized methods. It's a random projection, the other is a random computation. And another type is called learning to hashing. This means I use some machine learning technique to learn your data so that I can do a better hashing. So in fact, learning to hashing can generate a better accuracy because it tries to learn the data distribution to generate a good hash functions. Yeah, but so far there are three different ways: unsupervised, supervised, and semi-supervised. And the hash functions, the general form is expressed like this. So you can see h here. H is hk means the case hash function, and the input data is x. Given your data x, you can say it's a vector. This vector, x vector is your input, and this is your sign function. Sign function is just convert your result to be 0 or 1. To check if it's positive or negative. If it's positive, it will be 1. If negative, it will be 0. Okay. And the f function is a pre-specified function. It can be just a linear function or anything, or activation function, anything you want. Okay, you decide by yourself. And the w and the b, they are your hash function, or we call it a projection function. You can imagine that it's just like a projection. Given you x, and then you just time with your w, your weight, and also plus with your bias intersect, and then you can generate the number here. Okay, it's just to perform projection. Okay, so it's a general expression for hash function. So any problem? Okay, so give an example to index by using the hash tables. Okay, so in this case, you see we have 4 different hyperplanes, four different lights. You say use different colors. We have several points. So please note we have note the x1 here, x2, and the xn. And then we generate 4 different hash functions. So h1, h2 here, and the h3, and the h4. Okay, we have 4 different hash functions. So we can generate 4 bits. So let's check first one, x1. x1, we can see we just input x1 to the h1 function to see is 0 or 1. Okay. So for example, if for this side is below, we will encode it into 0. Okay, so this one h1, x1 is encoded as 0 here. Its first bit is 0. For the second point, x2 is also belong to this side, so it's encoded as 0 too. For xn, it's also belong to the right side. Okay, so it's encoded as 0. We just repeat the same way for the h2. H2 is here, and the x1, x2, xn encoded as y, bit y. And for h3, okay, h3 is here. Okay, all x1, x2, and xn they belong to the upper side, so they are encoded as 1, 1, 1. We check the third bit. Okay. For the fourth hash function here. Okay, there are some difference. You see, x1 and x2, they at different sides. You see, so they were encoded to a different bit. One is 0, another is 1. Okay, so for each point, we just according to your hash functions to generate the binary codes. And use this binary code, we can generate an inverted file like this. So the inverted file 0, 1, 1, 0, you just record, you just treat this as a bucket. So any point, the binary code is 0, 1, 1, 0, or you put it in this bucket. So it's called an inverted file. Okay, so it's the same to call IDF. Okay, so you can see S1 and Sn, they put in 0, 1, 1, 0 bucket. X2 put in the next bucket. Okay, any comments? And for your search, okay, give you a query Q. The Q will also is also a vector, right? So I put a vector to my hash functions. So I have several the same. I will use the 4 hash functions to generate the binary code here. This is the binary code is 0, 1, 1, 0. Okay, so I will make a constraint so that I hope the radius, the search radius will be Hamidis to be 1. Okay, so it means I can allow there are 1 bit different to the query. Okay, so you can enumerate all the binary code here. So first is 0, 1, 1, 0 is identical to the query, and then the second one I just change. I just flip from 0 to 1. 1, 1, 1, 0. Okay, so only you can see there are only 1 bit different. Okay, because I will allow the having distance to be smaller than 1. Okay, so I just enumerate all the possible binary codes here, and then for each binary code, I just check my inverted file and then check all the data, return to a 0 result. Okay, any problems? So the computation is just taking distance to compute between the 2 binary codes. It's identical to compute the Euclidean distance. Okay, and but compute the Hamming distance is more efficient to than the Euclidean distance. Okay, because Euclidean distance you have to compute the square and the square difference and with the root, right? But if you compute the Hamming distance, you just use XO and compute how many bits are counted as 1. So it's very simple. There are some hardware operations supported, so it can be computed very fast. It's very, very efficient than compute the Euclidean distance. So it's the main advantage why we want to convert the data to hash, to binary code, because the computation can be very efficient. But the accuracy is not as good as the Euclidean distance. Okay, I think it's trade-off. And also the space complexity can be very efficient. So suppose you have n d-dimensional real value vectors. You need 8 ND bytes to store your data. But if you use k-hash functions to generate binary code, your space need is nk divided by over 8 bytes. So here is an example. You have a 1 billion 96 dimensional descriptors. Okay, so if you use for the 96 dimensional vector, if each dimension uses 8 bytes to encode the floating point, you need more than 700 gigabytes. But you convert you just use 256 hash functions to generate only 256 bits. This means 32 can be converted into a 32 bytes, right? So we only need 32 gigabytes to store the whole database. So very efficient, right? Memory efficient. Okay, so it's another key advantage by using a hash function. By transform your data to the binary vector. Okay, I will stop here.